this module, you will learn about the periodic trends in chemical properties of elements. You have learnt that the reoccurrence of similar outermost electronic configuration after certain regular intervals causes periodicity in the physical properties of elements. Now let's see how periodicity affects the chemical properties of elements. Oxidation state is one of the periodic properties of an atom. According to IUPAC, an oxidation state can be defined as a measure of the degree of oxidation of an atom in a substance. In simpler terms, it can be defined as the number of electrons that have been removed from an element called positive oxidation states, or the number of electrons that have been added to the element, called negative oxidation states. So, the oxidation state of a monoatomic ion is equal to the net charge on the ion, positive or negative. The oxidation state of any element in the uncombined form is 0. So, oxidation states are typically represented by integers that assume positive, negative, or 0 values. How do you calculate the valence or oxidation states of elements? They can be deduced from the outer electronic configurations of elements. For representative elements, it is usually equal to the number of electrons in the outermost shell and or 8 minus the number of outermost electrons. As can be seen from the table, for representative elements belonging to groups 1, 2, 13, and 14, the oxidation states shown by elements is given by the number of valence electrons. However, for groups 15 through 17, the oxidation states are given by number of electrons in the outermost shell and or 8 minus the number of valence electrons. Transition and inner transition elements exhibit variable oxidation states. Along with transition, elements also show the oxidation states of inner transition elements. Now, let's understand the role of oxidation states of individual elements during the formation of compounds. The number of atoms of each element required for compound formation depends on the oxidation states of the elements. For example, magnesium belongs to group 2 and therefore shows an oxidation state of +2, whereas oxygen belonging to group 16 has an oxidation state of -2. Therefore, one atom each of these two elements are required to form a compound. Hence, the formula of magnesium oxide will be MgO. Note that magnesium oxide is an ionic compound, where magnesium loses electrons and oxygen gains electrons. Also note that the sum of the oxidation numbers of all the atoms or ions in a neutral compound like magnesium oxide is 0. But what happens in case of covalent bonding, where elements only share electrons, not gain or lose electrons? The oxidation state exhibited by an element in a covalent bond is equivalent to the charge acquired by its atom based on its electronegativity with respect to other atoms in the compound. The more electronegative element in a compound is given a negative oxidation state, whereas the less electronegative one is given a positive oxidation state. For example, in case of chlorine oxide, oxygen has a greater electronegativity as compared to chlorine. Therefore, oxygen atom shows an oxidation state of -2, whereas the two chlorine atoms show an oxidation state of +1 each. Now, let's take the case of oxygen difluoride. Recall that fluorine is the most electronegative element on Pauling scale, and therefore has a greater electronegativity than oxygen. Therefore, when fluorine combines with oxygen, the two fluorine atoms show an oxidation state of -1 each, and oxygen shows an oxidation state of +2. Some elements always have the same oxidation state in their compounds, with few exceptions. As we move from left to right in the periodic table, the oxidation number of the elements first increases and then decreases. As explained earlier, the oxidation number in a group remains constant and depends on its generic electronic configuration. The number of oxidation states, however, is the individual property of each group. You can observe periodic trends in the oxidation states of elements based on the formulas of their compounds, with hydrogen and oxygen. As true for oxidation states, all the elements in a group of periodic table show similar chemical properties. However, the elements in the second period do not share many periodic trends with their other group members. These elements include lithium in group 1, beryllium in group 2, and boron to fluorine in groups 13 to 17. Lithium in group 1 forms covalent compounds unlike other alkali metals that primarily forms ionic compounds. The behavior of lithium is more similar to the second element of group 2, magnesium. Similarly, beryllium behaves more like aluminium, which is placed in the third period and group 13. This similarity in properties found amongst the elements that exist diagonally to each other in the periodic table is called diagonal relationship. This anomalous behavior of second period of elements is because of three main reasons. 1. Small size. 2. Large charge to radius ratio. And 3. High electronegativity of elements. Small size means greater attraction between the nucleus and the valence shell electrons. So while forming compounds, the atom tends to share its electrons with other atoms, rather than losing them completely. Large charge to radius ratio means that the ion of the atom has a higher charge sitting on small-sized atom, a condition that favors covalent bonding. High electronegativity means that the atom has a higher attraction for shared electrons. This again makes covalent bonding favorable. In addition to the previous reasons, the availability of lesser valence orbitals and the peculiarity of the bonding capabilities of second period elements also contribute to their anomalous behavior. The first member of each group has only 4 valence orbitals, 1 2s and 3 2p orbitals available for bonding, whereas the second member of the groups have 9 valence orbitals, 1 3s, 3 3p and 5 3d orbitals. As a result, the maximum covalency, or the number of shareable electron pairs, of the first member of each group is 4, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. For example, boron can only form single charge ion with fluorine, whereas aluminium can form higher charged ions with fluorine. In addition, the first member of p block elements has special bonding capabilities as compared to the other members in the group. They have a tendency to form multiple bonds, as in the case of carbon and nitrogen, and to other second period elements compared to subsequent members of the same group. You have now reached the end of this module. In this module, you learned that oxidation states of an element can be deduced from its electronic configuration. For representative elements, oxidation number is usually equal to the number of electrons in the outermost shell, or 8 minus the number of outermost electrons. Transition and inner transition elements exhibit variable oxidation states. Oxidation state of an element in a compound is as the charge acquired by its atom based on the electronegativity of other atoms in the molecule. Oxidation number of the elements first increases and then decreases across a period. The oxidation number in a group remains constant and depends on its generic electronic configuration. The number of oxidations stated depicted by the elements varies with groups. The second period elements show differences in some properties from the other elements in their respective groups, and similarities with the elements present diagonally across them. The anomalous behavior of second period elements is due to smaller size, larger charge to radius ratio, and high electronegativity of these elements as compared to other members in the group. The availability of lesser number of orbitals and the peculiarity of their bonding capabilities also contribute to the anomalous behavior of period 2 elements.